Welcome to today's lesson. In this tutorial, we will solve absolute value equations by graphing and algebraically. So we're in the first half of section 1.7, and we're going to be graphing absolute value equations first. So let's review how to do that. Here's our absolute value equation. We're going to graph by transformations. I need to know what A is, what H is, and what K is. So A is always the number that's being multiplied to our symbol, which in this case is just a 1. So it's just going to be our normal output pattern. H is always the opposite of the symbol that you see here. I see x minus 2, so H must be positive 2. And K is the number that you see right there, which is negative 2. H and K combine together to make my new starting point. So 2, negative 2 is where I'm going to start. I'm going to put a little star here. And then my normal output for an absolute value is just, I can use this as a slope, at least on the right side. I can go up 1 over 1, up 1, right 1, up 1, right 1. And I've got the right side of my graph. And then I just need to remember that this is going to make a V, so I'm going to be doing the opposite on the left side. So up and left 1, up and left 1, up and left 1, up and left 1, and I'm going to do as many points as I can, and that is the left side of my curve, of my absolute value. So we've already graphed these. We've already had plenty of practice with that. So that's review. Now I'd like to focus on what are the zeros? In other words, what are the solutions? In another word, what's the roots? Or lastly, what are the x-intercepts? Remember, all four of these words mean the same thing. And if I'm looking for that, I'm looking for where it crosses the x-axis. These are the two solutions. These are the two roots. These are the two zeros. These are the two x-intercepts. So I'm going to say 0, 0, which is right here, the origin, and this point over here, which is 4, 0. Some people are just going to say that x equals the 0 and x equals the 4. That's fine. The x-intercepts we could write as ordered pairs. When we're looking for solutions to the equation, we might just say that x equals the two numbers that are the x-intercepts. So 0 and 4. Let's remind ourselves how to do this guy. It's the same thing. I'm going to find A, H, and K first. In this case, A is a negative 3, so that's going to change our outputs. H right here is going to be a negative 2, and K is the number that we see there, which is 4. I'm going to start at negative 2, 4, using my H and my K, so left 2 and up 1, 2, 3, 4. I like to put a little star just to signify my starting point. Now my slope, at least on the right side, is going to be negative 3. Or negative 3 over 1 if you'd rather see it as the whole fraction. So down 3 and right 1, down 3 and right 1, down 3 and right 1. And I've got the right side of my absolute value, V. And I just need to remember that it's going to be the mirror image on the left side. So I'm going to be going down 3 again, but this time left 1, down 3 and left 1, down 3 and left 1, and I'll get the other points to make my V. So my question again, what are the zeros? What are the solutions? What are the roots? What are the x-intercepts? Well, I see where they are. They're right there. But in this case, they're not nice integer coordinates like over here. Here, I know that it's in between negative 3 and negative 4, but I don't know exactly what it is. I know that this one is in between negative 1 and 0, but I don't know exactly what it is. So we need to solve algebraically, which means we need another technique. Graphing is only going to help us to solve the ones that have nice x-intercepts. When it's going to be in between two integers, we need another technique, and that's why we're going to be solving algebraically. So let's review our steps for how to solve algebraically an absolute value equation. The first and most important step, your absolute value bars must be isolated. Isolated means all by themselves, or all by itself if you think of it as one thing. Your absolute value bars have to be the only thing that's on the side of the equation. So we'll have absolute value and then equal to something. So we have to make sure that we isolate before we do anything else. Once we do that, we're going to remove the absolute value bars by splitting into two equations, and I'll explain how to do that. Once we've done that, we'll have two equations. We're just going to solve each of the equations. We'll solve for our variable. And then number 4, we have to check for what are called extraneous solutions. And this is our vocabulary word. Extraneous means does not work. I'll say does not work in the original equation. An extraneous solution is a solution that looks like it might work, but it actually does not check. It's an extra answer that does not work, and we have to make sure that we cross that out. So it does not work in the original equation. So here's our first example. We have the absolute value of 2x minus 5 is equal to 9. My first step is my absolute value bars must be isolated. They must be all by themselves. They must be the only thing on one side of the equation. And that's true. We already have it. It's all by itself. There's nothing attached out here. There's nothing attached out here. So we're good to go to step 2. Remove the absolute value bars by splitting into two equations. So every time we have an absolute value equation, I'd like for you to show a little split into two different equations. The first equation is going to simply state that 2x minus 5, the expression that's inside the absolute value bars, can be equal to 9. Because of course that's true. Absolute value, we could take the opposite of what's in here and set it equal to 9 as well. So the second equation, I'm going to take the opposite of 2x minus 5 and say that that could be equal to 9. And those are my two equations. The first equation is simply just writing exactly what we see without the absolute value bars. And then the second equation is slapping a negative sign onto this expression. Remember to have that expression in parentheses, and saying that the opposite could be equal to 9. And those are my two equations. I just need to solve them. So in this case, I'm going to add 5 to both sides, and I'll have 2x is equal to 14. And then, of course, divide by 2. I'll change color for each step. And I have that x is equal to 7. I'll check that in a minute. In this one, so I've got a couple different things I could do. I could distribute this negative into this expression to make negative 2x, and then plus 5 is equal to 9. Or I could just divide the negative away. I'll model that in my next equation probably. So now I'm going to subtract 5 to get rid of that number, and I'll have negative 2x is equal to 9 minus 5, of course, is 4. And then divide by negative 2 to cancel out the negative coefficient, and I'll have x is equal to 4 divided by negative 2 is negative 2. So these are my two possible answers. I should always mentally check to make sure that they work. So if I plug a 7 into the original equation, 2 times 7 is 14. 14 minus 5 is 9, and the absolute value of 9 is equal to 9. So I know that that one works. Plug in the negative 2. Let's see if that one works. 2 times negative 2 is negative 4. Negative 4 minus 5 is negative 9. The absolute value of negative 9 is still positive 9. Remember, absolute value is the measure of a number's distance from 0 on the number line. So they both work. And that's how you solve an absolute value equation algebraically. So let's look at our next one. Here's our absolute value equation. Now we do have a problem here. Our absolute value bars are not isolated yet. We have a negative 3 multiplied to them, and we have a positive 9 added to them. So I need to isolate by getting rid of everything that's on the outside of my absolute value bar. So I'm going to subtract 9 first, and I'll have negative 3, and then my absolute value bars is equal to negative 9. Still not finished. I have this negative 3 to deal with. Since it's being multiplied, undoing it would have to be by division. and now it'll go away. I'll have the absolute value of x plus 2 is equal to 3. Now my absolute value bars are completely isolated. You cannot do anything with the expression that's inside the absolute value bars until these are isolated. Think of these as, bricks, brick walls. We cannot enter these until they're all by themselves, and then we can split up into our two equations. So the first equation, we just simply use the same thing, x plus 2, and set it equal to the 3 that we see. The other equation is going to be the opposite of the x plus 2 is equal to 3. That's how we set up our two equations. And now we simply solve them. This one's going to be subtracting 2. And actually, that's the only step we have. So x is equal to 1. I'll check that in a minute. This one, we could distribute the negative if we want to, or just understand that this is like a negative 1. It is a negative 1 multiplied to this. I could just divide it away right now if I wanted to. And now it's gone, and I just have x plus 2 is equal to negative 3. So feel free to distribute and then solve, or just get rid of the number first and then solve. It doesn't really save you any time. It's the same number of steps. It's just a different order, I guess. So now I have x is equal to negative 5. So these are my two supposed solutions. Let's check them. Let's plug in a 1. 1 into the original, of course. 1 plus 2 is 3. The absolute value of 3 is 3. Negative 3 times 3 is negative 9, and negative 9 plus 9 is 0. So it does check. Yeah. Let's try negative 5. Negative 5 plus 2 is negative 3. The absolute value of negative 3 is still positive 3. And then we're back to negative 3 times 3 is negative 9, plus 9 is 0. They both work. All right. Moving on to example 3, which is the fastest example on this note sheet. We have the absolute value of 5x plus 3 is equal to negative 4. These bars are isolated. They're the only thing on this side of the equation. So we could start right into solving, or we could just use our logic and say, wait a minute, absolute value will never be equal to negative. Whether it's a negative 4 or any other negative number, absolute value is never negative. So if you have an absolute value set of bars and that's equal to a negative number, you know that there will be no real solutions. There are no answers. Some people just simply put the null set symbol, and that's the fastest way to write that. You could write the words no real solutions, or you could write the null set symbol. There are no numbers that would work for this equation. So that's a pretty easy one. Once you've isolated your absolute value, see if it's equal to a negative number, because if it is, you're basically finished. Just tell me that there's no solutions. Once you've isolated your absolute value bars, if it's equal to a negative number, then you're finished. If it's equal to a positive number, well, then you'll split up into your two equations and you'll go and find your two answers. Okay, so this is a little bit faster when it's equal to a negative. So we're finished with example 3. Example 4, what if we got some variables on the other side? So the good news is our absolute value is already isolated. We don't have to worry about that part. But the tough news is we've got variables on this side, and that's going to make our equations a little bit tougher. But once they're isolated, we know we can split up into our two equations. So let's write the first one. The first one is exactly what you would see without the absolute value bars. So x minus 3 is equal to 3x minus 5, and we'll solve that. Or we're going to take the opposite of the absolute value bars. The opposite of x minus 3 is equal to 3x minus 5. And those are my two equations to solve. So let's solve. Since I have variables on both sides, I need to pick one side to put the variables. Some people will subtract 3x over to here and make a negative 2x. Some people subtract the 1x over to here to make a positive 2x. It doesn't really matter to me, but I personally like to have my variables on the left side of the equation. So I'm going to choose to subtract 3x over to here, even though it's going to be a negative 2x. I can deal with the negative 2. I still have my minus 3, I'll deal with that next, and I have a negative 5 here. My next step, since I chose the left side for my variables, I might as well choose the right side for my numbers. So I'll add 3 to the right side. I'll have negative 2x is equal to negative 2. And then one last division, get rid of the coefficient, and I have x is equal to 1. I'll come back and check that. Let's solve this equation. I don't know if you'd prefer to distribute first or if you'd like to divide by negative 1. In this case, I'll go back to distributing. Negative x and then positive 3 equals to 3x minus 5. As long as you're showing your work, it doesn't matter which way you go for that. And here I'm going to subtract my 3x. Again, I'm pretty stubborn. I like my variables to always be on the left side of the equation. I don't care if they're going to end up being negative over here. I'll deal with that when I need to deal with that. Here's my negative 5. Now let's get rid of that 3. It's a positive 3, so I have to undo it by subtracting. And I have negative 4x is equal to negative 8. And I'll divide here by negative 4. And I've got x is equal to negative 8 divided by negative 4 is 2. So apparently I have my answers 1 and 2. Now let's check. Let's start with the 1. Let's plug a 1 into here. I get 1 minus 3. 1 minus 3 is negative 2. Absolute value of negative 2 is positive 2. Okay? When I plug a 1 into this side, I get 3 times 1, which is 3. And 3 minus 5 is negative 2. But wait a minute. 2 does not equal negative 2. This is not a correct answer. It's an extraneous solution, an extraneous answer. So I'm going to put a big X through that so everybody knows that I know this is not a correct answer because it doesn't check. Let's check the 2. Plug the 2 in here, I get 2 minus 3 is negative 1. The absolute value of negative 1 is positive 1. When I plug the 2 into this side of the equation, I get 3 times 2 is 6, and 6 minus 5 is 1. 1 equals 1, so therefore this 1 does check, and I'll box it in, and this answer, or this equation only had one solution. The other one was extraneous. So we looked at 2 graphs to solve graphically, and now we've looked at 4 equations that we solved algebraically. We have one last question, and I'm going to make it a try question. I'm going to have you do this. Try 1. For the equation absolute value of ax plus b is equal to c, describe the value or values of c that would yield these 3 cases. What would c have to be to have 2 solutions? What would c have to be to have no solutions? What would c have to be to have only one solution? Why don't you pause the tutorial at this time and answer this question by yourself, and then you can unpause it and I'll go through the answers with you. Pause now so you can try it yourself. So thanks for trying this problem. We're looking for the values of C that would yield each one of these cases. We looked at a couple different examples today where C would yield 2 solutions, and that is for any positive number. If C is a positive number, then we're going to have 2 solutions. We saw one case where there were no solutions, and that happened when C was a negative number. If C is a negative number, again, once the absolute value, of course, is isolated, then we'll have no solutions. So if a positive value yields 2 solutions and a negative value yields no solutions, then there's only one other number left, and that will yield 1 solution if C is 0. If you have an absolute value that's equal to 0, then you will have only 1 solution. So thanks for playing that one, and thanks for watching this tutorial. We'll practice more of this in class, and I'll see you then. Bye.